Addressing is a very important aspect at network layer. You must be wondering what is there in addressing. It's just a bunch of bits. Trust me, there is a lot, not just in this video. We will see this in the next few videos as well. But first, a few questions. So here is the problem we are trying to solve with respect to addressing. The addressing we have seen so far, the MAC addresses fall under this flat category. Basically, there is no structure as part of the addressing. Each network adapter does have a unique MAC address. Some portions of it is dictated by the manufacturer ID. If you take two contiguous MAC addresses, one can be used in India, another can be used in America. So what this translates to is for a router in the internet core, if there are n hosts, it needs n entries in the table. And if these hosts are in millions, you will need million entries as part of the forwarding table. And as mentioned in the router design, the address lookup becomes a major bottleneck. So if you want ultra fast download support for online gaming, all this would not be feasible to support, because for this you need switching in gigabits per second range, which won't be possible if the lookup becomes a bottleneck. So we do need a method of reducing the entries in the forwarding table for scalability purposes, especially when we are dealing with millions of hosts. As always, when we are stuck with a problem, we look at the postal system. How do you think the postal system handles this particular problem? So what I am about to say is not the way postal system handles, but just for argument's sake, suppose postal system did forwarding based on this. So each person, you represented him with his ancestry. Suppose a postman, let's say in Egypt, is sorting mail. He says, okay, Vijay, son of Ajay, grandson of Ajay, I have to send this mail out via Air India flight. Rinki, daughter of Pinky, okay, fine, Air India flight, so on and so forth. So this is the way he has to sort. So he has to maintain one such table, which will include the names of every person that is there in the world. Really stupid, right? To just send one mail to figure out where to send it on, he will take days to figure out on which flight to send. So the way things are done in reality is roughly like this. So addresses are in this particular fashion. So I've represented it in this way. So the postman just looks at this portion of the address and decides, okay, this mail has to go to India. India means Air India flight. So the entries he is maintaining is just this. India, you just have to take Air India flight. How many ever people are there as part of India? All of them will have the first portion corresponding to India. You just need to look at this portion of the address of the mail to conclude where to send the particular packet. So here, for example, at that particular postman, all he will have is a list of countries. And this is a very small number, which is very easy to manage. So you got the general idea of how to reduce the entries in the forwarding table. In the earlier case, your forwarding table had to include all the people in the world. Here, your forwarding table just had to include the list of countries, which is a much smaller number. So MAC addressing is like this, and IP addressing tries to copy this. So we'll see how it does. So to handle scalability, IP addresses have a structure to them. So this falls under the category of hierarchical addressing, where the address captures location in the network topology. So basically the 32 bits of the IP address consists of two parts. One is the network and one is the host part. Note that the postal address have different levels of hierarchy: country, state, city, so on and so forth, whereas here we are just sticking with two levels of hierarchy. One is the network portion, one is the host portion. The network portion identifies the network to which the host is connected, and the host portion uniquely identifies each host within this particular network. Now, how does this help? At a router in the internet core, an entire network in a given direction could be represented by just a single entry that corresponds to the network portion. In other words, if a network has, let's say, 30,000 hosts, you represent this entire network with just one entry instead of 30,000 entries as would have been required if the addressing were flat. Things will become clear as we go forward. So the next question is, we have these 32 bits. So how many bits should we allocate to the network portion and how many bits should we allocate to the host portion? There is a lot of diversity in life. Just like that, you will have networks of varying size. You will have some networks that have just 30 hosts, some networks that will have 30,000 hosts, some networks that will have 70,000 hosts. You need to cater to all these networks while at the same time ensuring that the number of entries that you need to maintain is kept small. Now, how can you do this? A simple but clever idea. So what you do is the size of the network and host part are not the same. In fact, they vary according to these classes. So class A addresses cater to those networks that have a huge number of hosts. In fact, they can support 2 to the power of 24 hosts as part of class A address. So how is this done? So you have 32 bits of IP address. For class A, the first bit will always be equal to 0 to represent that this is a class A address. Now of the remaining 31 bits, the 7 bits are allocated to the network portion and the 24 bits are allocated to the host portion. So how many class A network addresses, the emphasis is on network, are feasible? That's right, 2 to the power of 7, which is equal to 128. So the 7 bits can take on different combinations of zeros and ones. So you can hand out 128 addresses to 128 different networks or organizations that are managing these networks. Similarly, class B addresses always start with the bits 10, and again here the network portion is 14 bits and the host portion is 16 bits. So a class B address can handle 2 to the power of 16 hosts for a given network ID. And you can support 2 to the power of 14 networks as class B. And similarly, class C always begin with 110 and you have 21 bits allocated to the network portion and 8 bits allocated to the host portion. So class C is typically handed to networks that support smaller number of hosts. So as you can see, you are catering to different network sizes by accordingly partitioning the address space. So class D addressing, which starts with 110 with the number of remaining bits equal to 28, is reserved for multicast, and class E 111, it starts with this with 28 bits remaining, is reserved for experimental purposes. Each class of addresses also supports what is called private IP addresses. You must have come across these addresses before. So for example, this address space is used within IIT Bombay, likely in other universities as well. And this address space, you may have seen it if you have set up a Wi-Fi access point. These addresses are characterized as private because these are not allocated to any organization. In fact, if you have a packet with a destination address corresponding to a private IP address, it will not be routed as part of the internet core. In the public internet, this will just be dropped. So anyone can use these addresses without any approval. So in many places where it is not easy to get a public IP address, why it is not easy, we will see later, but those scenarios you end up using private IP addresses. So that's why we use it at IIT Bombay. Also at times you are given one IP address, the global IP address, as part of your service provider, and you have many devices within your home which you want to interconnect. In which case you could use a private IP address space to interconnect your devices within your home, and you use the public IP address to route the traffic from all these devices onto the internet. That is again achievable through what is called NAT. I will cover this again later. This 127 address belongs to the class A. So all these addresses in this range correspond to the loop back address block. In Unix or Linux, if you do if config, you will see an interface called LO, which stands for loopback interface. So this will have an IP address corresponding to this. So what are these addresses? These addresses are used for communication between networking processes within a given host. So since these are networking processes, they also rely on IP addresses, and this will permit them to communicate with each other without necessarily having to go out through the network adapter and come back in. So they just loop back. So when you get a packet, it doesn't really go out through the network interface, it just comes back. And again, you deliver it to the required process. So you see a lot of use for these when you do socket programming for testing and debugging purposes. So this figure puts whatever we have learned together. So we are dealing right now with just class C addresses. So as you can see, this network has been allocated the class C address where 216.12.1. In other words, all the hosts that belong in this particular network will have first 3 bytes corresponding to this. The last byte will vary from host to host. Notice that the router R1 also has an IP address corresponding to this particular network. Similarly, router R1 interconnects another network. Here, this is the address 216.12.3 was allocated for this particular network, and this portion stays the same. And similarly for this network, it is 216.12.2, and some other network that is far away has been allocated 222.5.11. So again, all the hosts within this, only the last byte varies. Now if you look at the routing entries corresponding to R1, it is not maintaining individual host entries. So all the hosts are represented by one single entry, which says that if the first 3 bytes of an incoming packet correspond to this value, send it out on interface 1. Similarly, the first 3 bytes of an incoming packet correspond to this, send it out on interface 2, and similarly for interface 3. Now if the first 3 bytes correspond to this is somewhere away, so it has to route it to that particular, in that particular direction it needs to route it. So it is going to send that packet to router 2, which in turn will forward it all the way till router 3. By the way, there is a lot of stuff. This is, let's say, the internet in between, and it will go all the way to router 3, which will again have some similar table, which will say for this, send it out on this interface. So the packet gets here. So among these 4 networks put together, you can have thousands of hosts, but the number of entries you have as part of the routing table is just 4. So this is the power of getting your addressing right. Reiterating more or less what I said. So every datagram that you are sending will contain an IP address of the destination host. And this IP address has 2 portions. One is the network portion, and another is the host portion. The network portion uniquely identifies a single physical network, and the entries in the routers are typically based on the network portion. And all nodes that share the same network part are in the same physical network. So that is the definition. And every physical network has at least one router that is connected to at least one other physical network. This is the definition of the router. Router has to interconnect 2 networks. So a physical network, if it didn't have a router, then it is unreachable. So it needs a router for it to connect to others. Now that we understand addressing, let's see how forwarding is done based on this addressing.